Alright, time for the DraftPhysics.com video presentation. So, a lot of crap to go over here. Anyway, so we'll start with dispar, go to PhysicistMichael, a couple of his comments, and then mindless marbles regarding the coupled oscillator, which she's somehow mocking. But anyway, we'll see. Dispar is doing the old Professor Lewin videos, and he's apparently going to spend a lot of time doing his little mathematical formula and saying that it gets all these accurate predictions and blah blah blah. And the predictions aren't all that accurate. It really is just kind of mushy. But anyway, what he won't do is a video about the concept itself, the very idea of creating free momentum and what that would mean in this universe, frankly. And the fact that when Professor Lewin did do the experiment, the carts couldn't possibly weigh what he said they weighed if you look at them. Appearances, it doesn't look very credible. Okay, let's just put it that way. The clay is kind of ugly, and it just kind of gives the impression of shenanigans. All right, so and then when he does the experiment without springs, when he's attempting to do an inelastic collision, and it ends up being an elastic collision, so again, those words don't mean much. There's no sign of this free momentum. Momentum is conserved. So without the spring, somehow momentum's conserved. So somehow springs are magical. So I'm going to talk a little bit about those experiments and what I think is happening, what the dynamics are. And so let's do that. I'd play this video, but there's nothing to play. It's analyzing a poorly performed, can't see much video of an air track doing masses that aren't even 2-to-1 or some sort of 3-to-1. They're not even nice round numbers. And they're certainly not the numbers you need them to do, which is the 4, 5, 6, 7, 8, 9, 10-to-1, where their theory predicts that you're getting almost twice as much free momentum. That one we don't see. All right. So they're saying that this little, simple m1 over m2 divided by m1 plus m2 kind of nonsense. So it's sort of like the relativity nonsense where they try to prevent an infinity from happening. But anyway, so it's kind of a simple idea, right? You have a one mass cart into the two. We'll do that example just because that's the most famous. Now, he showed the two mass cart hitting the one mass cart. I suppose that's worth demonstrating also. So maybe we'll do that one first. So you have a 2 mass hitting a 1 mass cart, and then you have an expected result. And let's understand there's springs involved. Now, elastic collisions, the formula is for elastic collisions. Clearly, metal against metal is elastic. So these carts should be able to just have metal hitting metal, and they should come up with the same answer. The spring shouldn't even be necessary. So the first question is, why is the spring necessary? What's its role to play? Now, you could also argue that these experiments could have been done hundreds of times by now with a Newton's cradle. 1 mass and a 2 mass, and it's the same idea. So why don't we already have these answers without air tracks? Why do we need an air track if pendulums could do it? We could see this miraculous free momentum happen. Well, I would argue that it doesn't happen. So you can't make it happen with elastic, collisions. Newton's cradle. Doesn't happen. Don't get any free momentum. So that's part of the chicanery here. As I've kind of pointed out, air tracks basically introduce another energy source, the air. Okay. And that extra energy is dangerous because a little tilt in the cart means that basically it has a jet engine, and it's going to make the cart move. And so you're capable of creating these kind of fakey and phony amounts of energy. But anyway, so let's just He says, I haven't provided any math. Well, I'm saying the math is you conserve the momentum, so what math do you need? But the rest of the math just has to do with this little magical spring. So let's just say that you did have a two-mass object, all right, in a Newton's cradle, and it was going to hit a one-mass object. What's going to happen, okay, to the velocity? This has a velocity of, we'll just say 1 to make it simple. So what percentages go where? So the idea would be is that as this one's momentum will decline, this one's will increase. And that's the conservation of momentum. So whatever this one moves, okay, in terms of a velocity, you have to subtract this total momentum from this total momentum. So whatever this moves, it's going to be taking it from this. So the idea would be is what you could theoretically say is that this might go the one velocity. So as it starts to push on it without a spring, it's going to get up to a certain velocity that's going to be the maximum velocity it can lose, okay, and give velocity to the other object based on its capacity to store momentum. Now it can't, let's say, make it go faster, so it can make it go the speed it's going. So it goes almost, so we could argue a little less than 1v, and this will go now obviously less than 1v because it gave away to this mass. So now the mass is half the value of this mass. To give this one mass, this would have to lose 1/4 of its energy. No other choice. I think 1/4 would be correct. Well, it's 3 altogether, so it's 1/3. Right, so I could make the same prediction as their prediction. So the 133 blah blah blah, except my answer is going to be more in the form of the momentum that you're going to be able to give the object, and you could argue that this would have 33 and this would retain 66 of what was 100. So if we start with 100 going in, 66 of it will stay in this object and 33 of it will go into the one mass object. And because this has the lighter mass, the 33% velocity, sorry, I should have said velocity, means, okay, that it will achieve the speed something less than, right, the original speed. So I guess it's probably better to use a bigger number, like a 10 or something. And you could just say, then I could just say this is going to be 8. Okay, and this is going to end up being 6 because that's all it's got left. So this will leave a little bit faster than this is going, obviously, because it gave it energy when it was going faster, and now it's losing energy. So its energy is going, its momentum is going down as this one's momentum is going up. So this one will leave going a little bit faster than this one retained. That's probably enough of that explanation. All right, so let's do the reverse. And, just put the spring in and say, okay, what is the spring really doing? So let's get rid of the air track. And so my argument would be is that when you're doing the two mass against the one mass, what you're really doing is doing it through this stupid spring, right? So because they use a spring, they're going to change how the experiment works in the sense that obviously as this one pushes into this one, the spring can only compress. If you were compressing against a wall that didn't move, obviously all of the momentum, the P in this object, would compress the spring. And then it would stop and all of the energy theoretically would be given back. But because this is yielding, that is, it's moving, it's saying I will move, okay? So it's not a brick wall. The spring doesn't compress as much. So the spring compresses less because it can't build up the pressure because this starts to move. So the one mass starts to move while the spring isn't finished and while this is still moving. Now obviously as it's compressing the spring, it's not really, it's sort of directional in the sense it's putting the pressure in this way, the spring can't expand back this way because this still has motion. It's still applying a force in this direction. So this starts to move. As it starts to move, the spring says things are getting easier because this is moving. So the faster this moves, the more the spring expands in that direction, because it can't expand in this direction. It can't go this way. It can only expand this way. And so it expands this way and gives this one a little more boost. So instead of the 33 number or something, you'd get some other higher number in terms of a little extra velocity, because you push the pressure in, the object starts moving based on when the pressure gets to the pressure to start it rolling, defeating its static friction. In an air track there really isn't any. But anyway, it starts moving it, and then as the spring, which compressed some because it isn't moving fast enough yet, so it first compresses a little and then it starts to expand, and it gives this one a higher percentage of that expansion, and then the other side stops and gets a push in the opposite direction. Well, that sort of makes sense to me. And again, remember, this cart is the 2 cart, and this is the 1 cart. Even though they're wrongly sized in this graphic. Yeah. This imperfect graphic, we will concede. All right. But, I mean, it's a real issue, okay? Using this word elastic to describe a spring or metal against metal, is that really rational? I mean, to have the same word for 2 completely different experiments, frankly. I mean, 2 really different circumstances. I don't think it's very rational. So anyway, so he doesn't take the formula to the obvious conclusion. What he ought to do is just write it out. Solve for all of them. So just show us that these are the predictions of their physics. So their physics basically predicts things like you start with 100 momentum in, okay? And as you increase the size, the mass of the object you're hitting, so you hit a 2 and then you hit a 3. I mean, I already did this. You hit a 4. Okay, you hit a 5. And you go all the way ... to 10 or some other number. And it just keeps going up. All right, so you get 33% extra this way. And then you get 44, you could say, okay, percent. And then you get 62% or whatever it would be. And you get 75%. All right. So you're essentially doubling the amount of momentum. So this is essentially 133 and 144, 160, 175. And we know by the time I get here, this isn't going to move at all. So we already know this has stopped moving. There'll be no sign of momentum in the object. This one, the other one will just bounce off. So they're sort of playing a game that the math won't work, because you're going to start getting a complete reflection. That is, you'll get 100 back long before their equation says you should get 100 back. This will stop moving long before. Okay, and this will go, you'll get a complete reflection before you're going to see this increase of twice the momentum. Before it gets to 200%, okay, going this way. All right, this way is already going to have 100% going back this way. So their math will fail. So if they do these higher differential, 2 to 1, 1 to 2 is what they're doing. Well, 2 to 1. Yeah. No, it's 1 to 2. 1 to 2, and then, do 1 to 3, 1 to 5, 1 to 7. Once they go up to these higher numbers, it's going to get more and more wrong. They're going to get more, the answers are going to get wronger and wronger and wronger. But we're not going to see any of those experiments, because they don't do any of those experiments because it doesn't frankly work. It stops, the formula stops working as soon as you start making this mass heavier and heavier. And that's a fact he's evading. Dispar. All right. So that's probably enough. I mean, I've been over this subject before, but I mean, it really is, it's almost a non-starter for us to talk about some formula for elastic collisions when they don't make a distinction between spring elastic, which should be called superelastic, and regular hard surface elastic. And again, even hard surface elastic doesn't mean much, as the anvil proves, right? So if I have a heat-tempered anvil, I can get 5 bounces of a ball bearing. If I temper it, okay, and create the impervious surface, the hard surface, I'll get 200 bounces. Obviously, the momentum is conserved in one case very well, and in the other case, there is real deformation. So even though it's steel, and it should be elastic, it's really not, because it's permanently deforming. It's leaving a little dent in the steel. And if you don't leave a dent in the steel, well, then you get all your energy back. And that's the obvious facts, all right, that they're ignoring, and they won't talk about those real theoretical physical facts, principles, like the conservation of momentum, like the idea that if I make something move in the universe, I have to apply a force. I have to use something's momentum. Things don't move for no reason. They move because they have to absorb something else's energy. There's no free movement in the universe. Nothing moves for free. It has to take the energy from something that has the energy. So off to physicist Michael comments. Alright, back. So, in this thread where mindless marbles and bass and bass are arguing not very effectively with each other, I guess I would say. But clearly what's being argued is this whole idea of creating free momentum, and the idea of negative momentum. That their math creates this nonsense where they can subtract this way from that way and somehow say something produced no momentum. That no energy had to be used to create the two motions, because somehow they're in opposite directions, and therefore we don't have to account for the energy that makes the action. So clearly in all these card experiments, this is the argument. You can't start with 100 in and then end up with 300 out. That is 200 going that way and 100 reflecting this way. It has to come from somewhere. You can't just make motion in the universe. So, yeah, those are very different theories of reality. And I argue that they don't have real evidence that any of these fakey kind of abstract experiments on air tracks are reflecting reality, because the experiment is so easy to do with a pendulum. And, obviously Newton had them, and Descartes had pendulums. Galileo had pendulums. They didn't make any of this crap happen. So why do we think it happens? All right, anyway. So physicist Michael, in that chain of conversation, where the real issue is, can't you use something better than a wooden stick? Okay, his answer is, I got a carbon fiber bar on order. So he's buying one of these. I think they're square. But anyway, carbon fiber things. Okay. I don't know enough about carbon fiber to say, yes, I guess it's supposed to be really inflexible, but we'll see. If it's here by Friday, this is the estimated delivery date, I will do my best to redo the experiment and get everything completed over the weekend. Doing this properly and clearly analyzing the data. Well, I mean, just doing it properly. I don't need your analysis, but thanks anyway. Editing it into a form that explains the principles at work, etc. Yeah, well, blah, blah, blah. That's all the stuff that's debatable, is your principles. Anyway, takes a lot of time and effort, so thank you for your patience. So, good. It's a concession that the experiment needs to be done better. Now, I would argue that you really should shorten the distance. There's no reason not to, because you don't gain anything. So I guess it's worth illustrating that part. Well, maybe I'll read the second comment, because that has some of this in it. All right. So the bass and bass guy says, I would suggest trying a non-hollow metal rod So again, the hollow part doesn't really matter if carbon fiber does have these properties of lack of elasticity, very rigid. Okay. Or even with DS suggestion of a metal piece on the edge, such as a ruler. It's good to have something. So yeah, even if you put a tiny metal strip, metal. I had a couple of things like that. It's a little stainless steel, tiny, thin piece of metal. Probably better to have that as the hitting edge, but doesn't. We'll see. Couldn't hurt, let me just say. You add very little weight and you're creating a very undentable or unvibratable surface, I suppose. Let's see. So I'm down here now. Okay. Non-hollow makes the mass increase dramatically, which I think would cause more objections. It's not about the objections, it's just a fact that a heavy lever means it's going to absorb more energy out of the experiment, and that's what we all both, I would think, would say is not a good thing. We want to try to make an experiment where essentially you could even create an oscillator where you could make it keep doing it over and over again because you're conserving all the energy. You don't have any places where you're losing it. Okay, I've already talked about the aluminum bar, which I don't know, you talked about it, but we didn't see anything. But that's already had some objections by DS, so that's a lie, essentially. I don't know where I objected to the aluminum bar. I haven't seen the bar. I'm still trying to figure out what this L part is. 1/8 by 1/2. I don't think I have a problem with an inch thick flat bar. I don't think that's going to flex much, but that's just my opinion. But that's already had some objections by DS and does still have some flex. I don't know, does it? See, I don't know anything about it. I didn't get to see any of it, but I certainly know that we don't need 36 inches of it. So that's the part where, again, might as well draw it. So, I mean, I wish you would sort of concede that, this isn't rocket science in the sense that we don't need micrometers and all kinds of things to get this close enough to write, and that it's really easy if you have if something's wrong, to fix it. So the simple argument is that this is what you're trying to do, right? You're just taking a bar and you're going to say, I'm going to hit it with something here, and I'm going to have something here. Okay, that's half the mass. Okay. All right, and it should get twice the velocity, okay, to compensate for having half the mass. I'm going to take the energy in here, the double mass. Oh, it's starting to rain. Anyway, a little bit of noise. So the expectation is that the momentum has to be conserved, and basically if you can do this efficiently, okay, then your expectation is that the momentum here is going to be the same as the momentum out, so you're going to have twice the velocity in a half mass object, and you're going to have 2x the KE, okay, and that's a problem. 2x the KE is not acceptable, okay. You have to conserve the kinetic energy, or the kinetic energy looks like a fake, okay. Just as in their experiments when they're creating the free momentum, I mean, clearly it doesn't make any rational sense. If you can make free momentum, then why can't we use that as a free energy device? I mean, momentum is a real thing. But anyway, all right, so what you're saying is, okay, what's sucking energy out of this experiment? Now, they're going to argue that this fulcrum can do something. Now, I'm going to argue that the fulcrum is really connected, as they kind of laughingly say, the Earth, okay? The Earth is what the fulcrum is, and that it isn't really going to absorb any energy. Any energy pushing on the fulcrum is just going to result in a pushback, just like your chair is pushing you back up right now. So the Earth isn't going to absorb anything. It's going to reject everything. All right. And so that's not going to be a source of a loss. So the loss really is just the motion of this mass. So the mass of the lever, okay, and the fact that it's going to be given a velocity that's a loss from these two objects. So that's the major downside. So the lighter the lever, the better. And you could argue that what's the downside? So now we're making an argument. Okay, carbon fiber, lighter. It's going to be 10 times lighter, maybe 20 times lighter than the things hitting it, maybe 50 times lighter. So it's going to be trivial in terms of how much energy it's going to steal from the experiment. And the other issue would be how much it's going to bend, and so it should bend very little. But any bending, the problem with bending is, maybe they'll acknowledge what the problem with bending is that it delays the transfer. So if the lever bends, that's a spring, and it essentially takes time for it to reflex back and do its thing, and that time is time it doesn't have. This is already left by the time the lever's gotten around to flexing energy in the other direction, so it's way behind, so it can't catch up and hit it when it's already gone. Obviously something can't hit something if it's already left, right? Right. Alright. So the argument is that you can do this experiment with a lever that's this long, or you can do the experiment with a lever that's this long. Now obviously, finding this 2-to-1 relationship, okay, of distances is made easier. The bigger you go, you can get this right down to the millimeter. But do we really need that much precision anyway? I mean, all it's really doing is saying that 2-to-1 is 1.999 to, 0.9999. It's only going to change it by a tiny factor. So even if this is a little bit off, or here, this is a little bit off, it's not going to make a huge, gigantic difference. So obviously, going with the smaller lever isn't going to hurt figuring out 2-to-1. Okay, one distance versus two distances is not going to be a challenging measurement. Alright, when you reduce the size. So not really an issue, frankly. So you're not losing much. And the whole point is if you did the experiment and you weren't getting 2-to-1 results, you weren't getting twice the velocity, you could always move it a little further in, or you could move it a little further out and see if it goes faster. Because if it goes faster, well, then you've matched the deceleration on this side to the acceleration on this side better. See, the fact is that it'll bounce. This will bounce if I bring this too close or I bring this too far. I mean, if I put it too far, it'll bounce because this thing gets too heavy. If I put it too close, this will go straight through and it won't use its energy. So the fact is, you can notice, you can see when you don't have it right. Because ideally you want this to come to a stop, alright, and you want this to have all the energy. So you don't want this to continue going, and you certainly don't want it to bounce. So if you see it bounce or you see it continue, then well, maybe I have to move this in a little, or I have to move this out a little. So that's a simple adjustment. So there's no crime against it. There's no argument saying, well, you can't move it so you get a higher velocity. Of course you can. And so you're just trying to match deceleration to acceleration minus whatever the lever consumes. Now the lever is still going to consume if it's carbon fiber, but it's not going to consume much. So ideally, make the experiment smaller. So he's using 2 tracks, and the simple argument is, why use the whole lever if it's bending? So if you have a problem where your lever's long and it's it's bending, okay, instead of staying rigid, well, it'll get stiffer as you get less far out. So make the lever much shorter, and then you'll have less bending. You'll consume less of the energy will go into distortion of the material, and so you're more likely to get your results. So he's basically got a track and a track. So just put the tracks closer instead of having the tracks this far apart, a meter, or 3/4 of a meter, whatever he's got. Cut it down to 12 inches. And yes, you can still get the 2-to-1 relationship. 1 unit of distance here and, 2 distances here. And so you can get your 2-to-1 relationship. So don't make it any, I guess the theme would be, is don't make it any bigger than you think you have to have continuity in terms of being able to get the lever to absorb the energy. Now the other argument is the fulcrum. As I've pointed out, he's using this geary thing, okay? And it's kind of a clunky it's not a precision gear. So it's a gear with these ball bearings in it, kind of heavy bearing. And my argument would be is that's all a place you can lose a lot of energy. It's number one, it's a heavy piece of metal. It's got a bunch of metal balls in it, which makes it even heavier. So you're not gaining anything using this fulcrum, because in principle, all you need is the pivot. You don't need to. This doesn't need to go in circles and spin efficiently. All you need to do is have a surface, a pivot point. So the triangle is a good example. You just want something for the bar to push against. So when you push this ball in and it hits, the pressure that goes here, okay, into this little point here, you just want to stop the lever, the center of the lever's mass. You want to prevent that center from moving the whole lever in this direction, and that's all you want to do. So all you need is a dent in this and a pivot, and then this can rock perfectly fine, all right, and do its job without you having the liability of moving a bunch of gears or metal or other crap. You make it as light as possible, and this has to be rock solid. This has to be tied hard to the earth. No flexible bits. If it's a nail that you're using, you got to use a thick enough nail so the nail doesn't bend, and yield. All of that kind of crap. But you want something firm, and you want this not to bounce too. So when the pressure hits, you don't want this fulcrum to bang into the, so let's say there's a little distance between the fulcrum, the part you've tied to the earth, and the part that's here on your lever, and there's a little distance there, and it bounces. Well, you don't want the jitter to happen, so you want to kind of make sure that it is forced, okay, the two are tied together, so the lever can't push away or push into. It just stays in contact with the fulcrum, and you can just, pivot. I mean, this big triangle is kind of a deception. You basically just want a tiny little notch, ideally. Like a crystal in a watch. They use little crystals in watches to create the bearings. And it's sort of the same idea. It's just something for the bearing, the wheel to spin on. But it's not a true, it's a bearing, but it's not it's not a complex one. It's a simple one. So keep the fulcrum as simple as possible and as light as possible, but as rigid as possible in unmovability. And that should also help, because that's the only other place you can lose energy. So all you really have is the movement of the bar can consume energy, because it's it's got to move in space. It's going to use up energy, or some sort of bouncing forces between things where you got a bunch of jitter or a bunch of something that's using up a bunch of energy. Motion. You're creating motion. You're trying to see. You want all of this stuff to move as little as possible. And you want the two objects you're testing to do all of the moving. So that is a rather lengthy explanation. Sorry, you missed everything down there. That's unfortunate. I should pay more attention to what I'm displaying as I'm drawing, but shit happens, as they say. So I will read further. Alright, okay, if I go with a smaller rod, we discuss those R distances. We decrease those R distances, right. So if we go with shorter, you decrease the absolute distances that you're using, but the effects should be the same. So it shouldn't matter whether the lever is a mile across or the lever is 10 feet or the lever, whatever it is, as long as it's 2 to 1, the action should be the same. And all you're really saying is that if you go with a smaller lever, it'll consume less of the energy. The errors introduced by off in distance is greatly increased. But again, those errors can't mean anything because you can adjust for them by just moving things in and out. And you'll see if the velocity increases, you haven't maximized the distances. And the distances may be off the 2 to 1 on purpose because some of the energy is being consumed by the lever. So some of the energy will require there to be a little bit tiny difference in the acceleration rate. if I'm using a 50 centimeter distance, being off by 0.5 centimeters isn't a huge deal. Still trying to minimize. But if I'm using 5 centimeter distance, that's a 10% error. So again, the error is kind of irrelevant. You just want to get as close to 2 to 1 as possible. So I don't see this as an issue. To say that it's, we're going to have enough error because it's a millimeter off, it's not going to be enough to ruin the experiment. It makes the angular momentum measure much higher error. So I argue the angular momentum is irrelevant to everything in this experiment. The only thing that's got angular momentum will be the lever. The objects are moving straight, linearly. The only thing that moves angularly is the lever. And I'd still argue, because of the law of the lever, the angular momentum is the same as linear momentum. There's really no difference. So it can't possibly change anything's results anywhere. All right. Which is the main thing that the textbook physics model says should be conserved in any collision. So again, I don't see how that's rational. It's clearly everything we're doing is to force it to be linear. And ideally, so I guess it's another subject worth mentioning, so I'll mention it since we're on the subject. Because, it's one more source of friction I forgot to point out. One more source of losses that should be pointed out. Let's see if this marker works. The other one's starting to run out. And where is my eraser? Oh, here. Alright. Alright, so the smaller the lever you make, the more the angular problem gets into it. The levers, you can obviously see it turning, right? Where if I make it very long, you don't see it really doing the turning thing, right? So the smaller, all right, that's a complete, throw that one out. All right, yeah, let's not bother with that. Is what it should be. Oh, let me try this purple one. I haven't done this one in a while. Yeah. All right. Where was I? So small lever means you can see it turning very easily. Where if you make it very long, you don't see the turning part. You just see the up and down part, right? So longer means it looks more up and down. Smaller means it's turning more. It's going this way more than it's going this way. All right. But it's really, I would argue, still not a hugely important factor. So you could sort of understand that if something's hitting the lever and it's going to move the lever, the point that it's in contact with the lever will change as the lever moves. So I'm going to hit this part. Because this thing's on tracks, this has to go straight. So what's going to happen is it's going to hit the lever first here, at this point, when this is flat, right? So this will be where it's hitting. And it's going to have to slide on the surface of the lever, and then it's going to be hitting here as the lever moves. So as the lever turns, this friction here is another point where you can create some losses. Now, a way around some of that is to put a stop on the lever. So when it hits, stop here. But the cart's not going to really stay on the track then. Okay, so you could have. So the lever would basically have a little stop on it, all right? And then if you caught the ball, it wouldn't be able to go this way, right? So it would go with the turn of the lever. The ball would follow that path. But because this is on a track, you can't do that. So you're going to have a little bit of this sliding problem. Now, there might be a way to overcome some of that by putting a bend in the lever or some other kind of, there might be a way to get around some of that. But I don't know if it's enough to be a problem. But it is something to be conscious of, that whatever the contact is here, it needs to be well oiled or greased or something, just so you don't have, so it slips across that surface as benignly as possible, because it is going to have to slide across the surface of the lever. All right, so I don't see it as a huge problem, but there's lots of problems that don't look like they should be a problem and they turn out to be a problem. I had a problem where I was just having a piece of wire with a piece of fishing line, and my assumption is, wow, the wire should swing on the fishing line really easy. But what you don't realize is fishing line has a bunch of crap on the surface, and it really doesn't slide. It's not a smooth surface, and it does hang. So, I mean, these things do come up. So it is something to be aware of. But I think what we're gaining in the lack of mass, you can afford to lose in the fact that your contact with a lever won't be as pure. But again, that could be totally wrong. I mean, this angle of contact isn't perfect. I mean, you're pushing on the lever in this direction, but the lever isn't getting pushed this way. It's getting pushed this way, which isn't ideal. All right. So 50 to center, I did a minimize. That's a 10% error. It makes the angular momentum measurements much higher error. It makes the angular momentum measurements much higher error, which is the main thing the textbook physics model says should be conserved in any collisions regardless of flex. So again, I don't really understand how any of that is relevant. Again, he keeps pointing out the angular momentum, and it just doesn't matter. I mean, the fact is, I can make a wheel where all the mass is out here, and I can make a wheel where all the mass is here in this ring. And I use spokes, and so it's 90% of the mass is in one place, 90% of the mass is in the other place. And I could argue that those two wheels will behave based on the fact that these motions will be different. It's more mass moving more distance. So this one will move twice as slow with the mass on the outside as the one with the mass on the inside. And that the relationship will be completely consistent with linear momentum in the sense that it'll just be a 2-to-1 relationship. There won't be a 4-to-1 or 10-to-1 or any other number to 1. All right. So let's see. As long as there are no external torques, angular momentums, again, this idea that there's anything in this system coming from the outside, I think it's just crap as a distraction. There really isn't. There's just going to be the force you put in, the motion, the momentum, and you either you waste too much of it or you don't waste too much of it. But that's all there is. All right, which is absolutely not the same as linear momentum. So he says they're not absolutely the same. I say they behave exactly the same. The law of the lever is basically anything rotating has to obey the law of the lever. So whether it's a tire on your car or whatever it is, anything rotating is obeying the law of the lever. Where the mass, the center of the mass is deciding rotation speed. So that's your average. So that's all you figure out. Where's the center of mass, the location of the center of mass, and it'll tell you exactly what the speeds have to be. So if you have twice as much mass on the outside, you're going to go twice as slow. And does exist for an object moving in a straight line. So again, I just find this almost incredulous, okay, because we know you're forcing the straight line with the track the carts are on. As long as it's not only moving along the axis we're measuring AM around. So again, I don't know why we would even bother measuring. All the angular momentum is just in the lever itself. If we make the lever light enough, then anything it's using or consuming is going to be not terribly relevant. Sorry for the nested parentheses in that last sentence. Yeah, it was a little bit hard to read. But anyway, I think it's a moot point. So the lighter the lever is, the lever's the only thing doing angular crap in this experiment. It's the only thing. And all you have are the contact points, and you try to make those as frictionless as possible, the fulcrum and the rubbing parts. And otherwise, nothing else has any angular issues. And even if you did make a bucket that the ball fell in and it did move in an angular rotation, we're right back to gears. We're right back to just saying, look, I can make a gear this big, and I can attach it to a gear this big, twice as big. And the fact is that I can put a mass on the small gear, and I can put half the mass on the outside gear, and they will weigh the same. And it'll take just the same amount of force to push both of them on their radiuses, on their circumferences. All right, so we've got enough of that, so we'll move on to mindless marbles. All right, back. So I had this drawing in my video talking about this coupled oscillator, and I pointed out this is how simple it is. There's just a piece of wire connected to the center of the lever, hollow aluminum tube. So just for clarity, this weighs about 1/50th of the weight of the two mass, let's say. This is insanely more heavy than this is, okay? Gigantic 50-to-1 kind of relationship. So the lever is very light by comparison to the total mass, which is very big. All right, these are solid half-inch steel bars, okay? So any motion up here really can't be taking much out of here. So you can't make some argument that when this one's moving, there's a whole bunch of momentum in this part up here that you don't see, and when this one's moving, there's no motion up here, you know, or some kind of nonsense, frankly. But yeah, I didn't weigh any of this stuff. All right, I'm just saying this is kind of obvious. This is half as big as this, so it's solid steel, so it's going to be pretty close to 2-to-1. And again, you can imagine a hollow piece of tubing. It might weigh 3 ounces. This weighs at least a pound or more. All right, anyway, 2 pounds. So that's it. And so all you do is you put the energy in here, okay, bang, all right, then this oscillates at a speed and a displacement, okay, of space, and then the oscillation migrates over here, it leaves here and it goes over here, and this oscillates with what clearly looks like almost twice the deflection, okay, and clearly looks like twice the speed at the maximum. All right, and the energy just keeps moving back and forth. Now, their theory says, okay, if I put 100 in here, I can't conserve the momentum over here. To conserve the kinetic energy, I have to kill some percentage of this momentum and say that this only has 1.4, okay, that it's not doubling the velocity. So essentially, it only has 0.4. Yeah. Let me see how to draw that. So say the velocity here was 10. This has to have a velocity that can't be 20. So it has to be 14 instead of 20. So instead of 20 for half the mass, it has to be 14. Okay, so you lost that much momentum. The difference between 20 and 14 is how much momentum you lost. So I should be able to figure that out. But anyway, the point is made, I think, okay, is that you have to lose momentum, and then when the energy goes back, I get my momentum back again. So somehow I have to lose the momentum to conserve the kinetic energy, and then somehow I have to put the momentum back again when it oscillates over here. And that's clearly happening because it's losing energy so slowly that obviously you get back like 98% of what you started with. You know, it's a very high, it's very conservative of the energy. So clearly I couldn't have lost, you know, whatever, 1/3, right? I mean, 66 of 2 would be like 1/3. I clearly can't lose 1/3 of the momentum and then put it back again, and then lose 1/3 again, and then put it back again. That's not very rational anyway. So they won't concede that that's not very rational. That's pretty much what it comes down to. So they're going to have to see more. They can't recognize that if it actually is oscillating, then it has to be oscillating with the same momentum on each side. And they think something else can be true that I can't personally understand. Alright, so I said I used a lever to create a coupled oscillator between a 1 mass and a 2 mass. I think you would concede. So I think a physicist would concede that a coupled oscillator has to conserve momentum. That a coupled oscillator cannot create different momentums on the two sides of the oscillator. All right. That momentum must be conserved in the coupling. I would like to hear if you have some explanation regarding how kinetic energy could be conserved. So that was my question to physicist Michael. So we'll see if he answers eventually. But mindless did. Okay, so he quotes me as saying, I think you would concede that momentum must be conserved in the coupling. So he says no to that. The masses are connected to strings that exert an external force on them. So he's saying that somehow the external force is gravity. And I would argue that if you analyze this, the gravity is always the same. The external force, okay. Oh, I didn't put the comment up anyway, so it's not in the way. The external force is this, okay? This is connected to the Earth, okay? And my argument is still the same. This says, what's the total weight of this experiment? That's all it cares about, frankly. There's nothing else happening here, okay? So there really isn't. It's all closed. There's no place. These always weigh what they weigh. That'll never change. And all you're really doing is changing the pushing this way and this way into each other, okay, by wobbling the lever. So the lever wobbles a little tiny bit of movement up here, and it leads to a lot of movement down here eventually, or the transfer of the movement. But you basically just have a single pendulum, in theory, swinging back and forth. And it would be silly to say there's an external force when a pendulum swings back and forth. I mean, who would bother with that nonsense? To say that the experiment is ruined. The pendulum can't tell us anything because there's some external force ruining the experiment. There really isn't. Alright. Let's see. So the masses are connected to strings. So again, they're not, it's fishing line, but regardless, that doesn't play a role. It's just some very light material that just holds the objects. It doesn't really play a role. It might stretch a little bit, might have a little elasticity in it, but it's not enough to make any difference at all. Okay, the masses are connected to strings that exert external force on them, so it's just nonsense. This is how the masses swing. It isn't really how they swing, but whatever. So just like with the lever, so he's saying this overtly, the presence of that force means there's no reason to expect the momentum to be conserved ahead of time. Of course, there's every reason to think it should be conserved. There's absolutely no reason you have no theory of where the energy goes. Okay, so you can say it's disappearing somewhere and then it reappears again. So, I mean, that's the trap you're in. Clearly, in this case, I'm not just shooting something and they're both, all the energy's leaving. It's a continuing, oscillating system. So it's like a teeter-totter in gravity, if you could make one. And you just keep putting the objects back into a circumstance where the energy is going to come back down again, and so it's conserved and it's an oscillator. Anyway, let's see. Momentum to be conserved ahead of time when it could be shared with the Earth. So again, there's obviously very little evidence. It goes on for minutes. Very little evidence that it's sharing anything with anything. The energy is staying in the pendulum. Okay. How exactly did you couple the two pendulums? As I explained, I coupled them with a lever. There's no springs. There's no other device. What I drew here is all there is. All right. Did you have a string between the two oscillators or something else? No. Is there any way we can get accurate velocity measurements? Well, I think there is. I mean, frankly, yeah, you can analyze it and see how fast things are going. I'm still going to argue that I think theoretically, there's no way the kinetic energy can disappear and then the momentum can exist, and then the momentum changes on the other side, it goes down, and then when it's transferred back to the other side, the momentum shows up again. I think that's a insane kind of moronic thing to believe can happen. But anyway, is there any way we can verify the masses of the objects? Is there some reason you need to do that? Make up a number. It doesn't matter. It's 2 to 1, kind of obviously. All of these details are completely omitted. Yeah, and I'm just saying that for the purpose of just creating a test of theory, that's all I want to do, okay? Again, I'm not the one suggesting I do these experiments. It's just kind of surprising that your physics has never done any of this. Your physics can't tell you the right answer, can't show you, because it hasn't videoed it, hasn't shown it, doesn't do it, doesn't care. All right, so that's why we're in this position. It's because your physics had 350 years to shore up your theory, and you haven't bothered. I mean, the simple experiment would be to prove it takes 4 times the fuel to go twice as fast, or 9 times the fuel to go 3 times as fast. But you don't show that. Bang something into a brick wall and see if it's going 3 times faster if it crushes 9 times as much. But you haven't done any of it. All right. So he has another comment on Brozo's channel about the same thing where he's ridiculing the whole idea. So I'll read that comment. Sorry, this is just funny. Well, anyway, the comment I'm going to read is on this other video, but Brozo's apparently made some 3-hour and 31-minute long video, and he titles it, Respond to Gary's latest long videos. Like, long videos are a bad thing, and he's making an insanely long video. So that's kind of funny. So I don't know. I don't think he'll have any hope of understanding what a coupled oscillator is. So he's actually going to play the coupled oscillator video. So I'll have to watch this first, just because it could be 3 hours. I mean, I'll have to try to just extract some notes about what his arguments are. But anyway, just amazing. Alright, so here's the mindless stuff. I didn't read all of this. I just noticed it and said, oh, he's ragging on this concept too. Alright, Gary had a new idea for an experiment recently, and I don't even know what he expects others to take away from it. I really don't expect, like I said, my expectation is you people are too stupid to know what a coupled oscillator is. I mean, you have to watch some of these videos on, physics lectures to really understand this coupled oscillator crap. And the mathematics is insane. I mean, frankly, I could show you a Professor Lewin video where he's got 3 boards worth of math just to analyze a simple coupled oscillator. So, but the basic bottom line is momentum is conserved through the oscillations. Okay. So anyway, yes, I see those 2 cylindrical blocks. So I don't know. Yes, pieces of steel transferring motion. They're clearly violating KE. So I don't know what he's talking about there. Okay, he's got that in quote. I don't. Where did I say cylindrical blocks? This isn't a quote of mine. I mean, what are you quoting? It's so bad. It's unbelievable. This cretin and his fans even have a right to talk about science with any certainty. So it's clearly, I'm showing a coupled oscillator, and I think showing it in a way it's never been shown before, with uneven masses, and the fact that they're moving towards each other. So I think it's really interesting, frankly, and you're just saying, fuck you, garbage, out of hand. I mean, when you probably, look, I'm just saying, you're probably smarter than the rest of these assholes. I mean, you might know what a coupled oscillator is ahead of time. But, what is this shit? Anyway, it's a funny thing happened on my way to the experiment, he says. Yes, and so he's quoting my, the text out of my video. I mean, I don't know who thinks this is a great idea. A fair concept, let's even say. And the fact that he can't reformat it is just amazing too. Okay, now I didn't bother doing frame rates. Yes, okay, so there's no point in me restating what I stated in the video. I think I made the video clear. I just realized I could do this thing. I created a crude experiment, and it basically does this coupled oscillator thing. So what's the problem? Why are you griping? All right. Those blocks are connected to strings. So this is the same shit I guess he put in the other comment. That exert external forces. So again, he's saying there's some kind of external force fucking up the experiment. That a swinging pendulum is being affected by the Earth, and all kinds of stars and galaxies are all fucking up the pendulum. When clearly it's not. Clearly, the whole point of the coupled oscillator is showing that the energy stays in the system. The fact that it goes on for minutes proves that the energy stays in the system. There's no added energy. There's no subtracted energy. Not a significant amount. Clearly it loses energy, but it loses it a tiny bit at a time. All right, continuing. So these blocks are connected to strings that exert external forces. So I understand there's no external forces. It's all contained inside of essentially one pendulum. Okay. This is how they make masses swing and change their motion. So there's no external force required to do any of that. If gravity and the strings are playing active roles in the motion of the masses, the only thing gravity is doing is conserving the energy. That is, obviously, with a pendulum, you're putting the energy into gravity in the sense of you're putting it into your position in a stream, and then the stream is going to push you again. So you're going against the stream of gravity, and then you're going with the stream of gravity. So gravity is like a spring. It stores the energy. Then here the external forces on those objects. Then there are external forces on those objects, so the momentum is going to be shared with the Earth. So it's just absolute baby talk. The Earth doesn't absorb half the momentum, and then when the other one's swinging, it's the Earth is absorbing half the momentum, and then when this one's swinging, it's the Earth isn't. I mean, it's just nonsense. Thus, there is no reason to expect momentum to be conserved. So again, he's saying there's no reason to think momentum has to be conserved when, yes, most of the physicists say, yeah, you have to show where it did any of that crap. If you're going to claim the momentum went somewhere and then came back again, you're going to have to show what the logic is. How did the Earth give it back? All right. If it can be shared with the Earth. So it's just, so he'll deny the lever. So even if you did the lever experiment, showed twice the velocity coming out the other side, it wouldn't matter to this asshole, because he's going to say the Earth gave it the extra velocity. The Earth created the extra kinetic energy. So we're almost back to their other argument where they argue that when the ball bearing is bouncing on the anvil 200 times, it's putting energy into the Earth each time it hits. So each time it hits the anvil, it puts 100 momentums into the motion of the Earth. So it moves the Earth, I don't know, 7,000 momentums worth. Anyway, a similar point was told to him by physicist Michael multiple times. What similar point? Over and over and over again about how the fixed pivot of the lever, which is keeping the damn thing from falling off and flying away. So again, this is more nonsense. I stated if you put the lever on the side of the space shuttle, you're saying it's going to move the space shuttle. I'm saying no, the space shuttle is not going to give a shit. It's going to just reflect the energy, period. What goes in one side is going to come out the other side. If you have 100% transfer, the space shuttle is not going anywhere. If the ball bearing bounces off the anvil didn't go anywhere. The Earth didn't go anywhere. That's why you got 100% back. It's because nothing moved, fuckhead. That's what I've said over and over again. And where is your coherent, rational response to that argument? That you have zero evidence that the things that aren't moving have momentum. So the things that you can experimentally know are not moving. You can't show them to be having momentum because they're not moving. The anvil isn't moving. You're claiming the whole Earth is moving hundreds of times, hundreds of little jolts. I mean, it's really just idiotic. Obviously, the energy is still in the ball bearing. Obviously, the ball bearing being shot back up into gravity takes energy, takes momentum to do that. If there's twice as much momentum going into the Earth, how can you possibly make sense out of that theory? Anyway. I've repeatedly made these points, and he's repeatedly ignored them and provided zero response to them. Okay. The damn thing from falling off and flying away, it's providing an external force, so it's not providing anything beyond what your chair is providing. That's it. It's just resisting your motion and saying you can't move. So the momentum will be shared with the earth, and it's shared in the sense that the earth throws it right back in your face. It pushes you back up, clearly, or whatever the lever is connected to. So it's zero sum. You don't gain anything. Gravity's pushing you right now into the earth, and every time it does that, the earth pushes you right back. Gary deliberately ignores this, so I don't ignore anything, so you're just such a fucking liar. I waste so much time going over all of these moronic statements by you trolly pieces of shit. Okay, and ends up asking PhysicistMichael the same question as if he never answered it. Well, where did he answer it? I'm sorry, where did he answer the question? How you cannot conserve both kinetic energy and momentum if you transfer energy from one object to the other object. Clearly, I'm making a 100% transfer in the experiment I'm showing. There's 100% transfer of the fucking energy. Undeniable, whatever the energy is. Okay, and the point is it can't be both. It can't be conserving kinetic energy and it can't conserve momentum. It can't conserve both because the masses are different. And that's an absolute fact that he hasn't dealt with at all. He has said nothing. Which really, really rude if you ask me. So it's rude for me to ask you to explain to me how if you have two uneven masses and you convert the energy from this one, the momentum, into this one. So 100% of the momentum has been successfully exchanged into the object, that they could possibly have the same kinetic energy. It would be impossible. So if I make it go into this one, and this one has the energy now, it has to have more kinetic energy. If it has the same momentum, it has to have more kinetic energy because the mass is smaller. Fuck. You stupid fucking piece of shit. Anyways, it's amazing how he wants to back away from any hard work. So any more bullshit. It's already been explained how, gee, yeah, it's not so simple to make a lossless lever. And what I found was, oh shit, I can make a lossless lever. I can do it if I use it as an oscillator. If I use the lever as an oscillator, I can make it lossless. Our due diligence that others have put in, blah, 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 blah. What put in? Where have you put in any due diligence? Where have you dealt with any of the arguments made about Deschardelet, any of the arguments about Leibniz, any arguments about the history of this stupid theory, any arguments about the fact you have zero fucking evidence after 350 fucking years of propagandizing about your silly Jesus, you still have nothing to provide as evidence. All right. He is just so fucking goddamn dishonest, you people are. Let's see. He wants to avoid doing actual velocity measurements. No, I don't. So again, just more nonsense. Just nonsense. Sorry, it's nonsense. I just wish to see, okay? I said I can, work on the experiment some more. It's not impossible to do. I hate doing it, but I'll do it. This is not my job, frankly. And, it's a huge just waste of my time, in my opinion. My work as a theorist, okay, is diminished by me having to do this experimental crap. But anyway, I have work to do on the simulation. There's all kinds of things I need to work on. But yeah, there's no problem. The velocity experiment's right there in the video, so I'm just saying, it's not going to be a big deal. I'll find a better angle to video it at and all that stuff. Which will be the most important part of the entire experiment. No, the most important part is the theory. I'm trying to get you to accept that you theoretically don't have any wiggle room here. So it's just like Brozo talking about launching things off of cliffs. There's no theoretical room. If something leaves the cliff with twice the velocity, it's only going to travel twice as far. It doesn't have a choice. Oh, fuck. All right, back. All right, so he wants to avoid doing actual velocity measurements. So as I pointed out, you can basically measure the velocity based on the arc. And that was the whole point of me making it as long as possible. So it's like 7 feet, right? So the pendulum is 7 feet long. And that's to take out as much of this, angular problem as possible. And you can basically argue that the longer the pendulum, the fact is the velocity becomes basically just a distance argument. It's just how far does it travel? How big is the arc it's cutting? So, it's really going to be easy to do the velocity measurements because all you're saying is the periodicity is the same with the two pendulums. And basically you're just saying that this one's moving twice the distance in the same time the other one's moving half that distance. So that's a pretty accurate way to understand the fact that it's twice as fast is because it's twice as much distance. So why am I showing a fear of doing velocity measurements when the whole point of having a very long pendulum was to do velocity was to make it easier, which would be the most important part of the entire experiment if he had to decide what is conserved, and he wants to avoid that. I posted both the links so you could go do it yourself. So nothing's stopping you. Whatever this is, ortho. I'm also glad he is sparing us from subjecting us to his frame rates crap torture. And Brozo's frame rate videos aren't torturous? I mean, he went through 23 cart thingies doing counting frames. Amazing what a duplicitous fucking hypocrite you are. Because it would be crap indeed. So he doesn't think frame rates are going to tell you the answer, but he needs to give accurate velocity measurements. So I'm just saying regardless, if I can show the arc of the lighter pendulum is twice as big, twice as large, it's pretty much proving that it's twice the speed if the period is the same. So if it's the same period, and it's moving twice the distance, well, that has to be twice the speed, doesn't it, fuckhead? Amazing. How exactly did he couple the two pendulums? Well, I explained it in the video. I drew this simple diagram showing exactly how I coupled the two. So, not complicated. Did he have a string between the two oscillators or something else? No, I didn't. That's the whole point. The lever is providing the compensation, the connection between the two sides. Is there any way we can get accurate velocity measurements? Well, you just talked about it. Frame rates is one way, but obviously you could also do crude measurements of the absolute distance of the period. If there are any way we can verify the masses of the objects, well, again, it's a piece of steel cut in 4-inch and 2-inch pieces, something like that. I'll weigh them, but I just mean it's going to be, I'm going to predict it's going to be damn close to 2 to 1. All of these details are completely omitted, and yes, on purpose, and as I pointed out, because I want to test you and see if you can understand that theoretically you don't have a choice, that you're in a theoretical dilemma. All right, because if the video's doing what it looks like it's doing, which is creating a perfectly coupled oscillator, and it's a very efficient oscillator, then what's your theory? Half the energy, 1/3 of the kinetic energy disappears, and then it reappears, and then it disappears, and then it reappears. Given his tendency to guess the weights of everything, I guess it's not a very tough guess, frankly. And the guess will be right. I'm just saying, what do you think the odds are that it's going to be really far off from 2 to 1? A piece of solid steel rebar cut to inch lengths. What's the odds that one will be more than 2% off of 2 to 1? As we have seen recently in his scale that he admitted is garbage, it's garbage at weighing things outside of its range of ounces, a few ounces. I wouldn't even trust the weight measurements. Frankly, I wouldn't even trust him if he said the sky was blue. So again, yes, I have been demonstrated. Somebody has real evidence that I faked something or phonied something somewhere, which is just an outrageous lie. In fact, that'd make me think something must have happened to the sky. So again, you're the ones defending experiments with clay all over them. Okay? You're defending Brozo, who my prediction is 12, his prediction is 16. He gets the answer of 14 and then says he wins. He gets an irrational, useless answer, completely noise answer. I mean, obviously an error answer, and claims victory. And that's the person you do trust? You're a fucking idiot. But I already pointed that out. It's already a proven fact. So Brozo says, I've not yet seen any of the nonsense from Gary. So again, coupled oscillators is a nonsense subject. I find it objectionable even listening to him anymore. So what? I find you vomit-worthy. Big fucking deal. Since he proved himself to be so blatantly hypocritical. So again, another lie. And then he says, and boring. Compared to what? I mean, compared to your childish nonsense? Ugh, to be frank. I'm suffering with intense back pain. Good. I mean, get what you deserve, frankly. Okay? That sounds like one of the things you deserve. Slow death would also be nice. Sciatica at the moment, so it's doubly hard to motivate myself. Well, motivate yourself to what? Slander other people and lie, you fucking little Weasley cheater. I mean, did you lick anybody's food at the grocery store today? I'll give it a go, though, so I can properly understand what you're referring to. So isn't that hilarious? Yeah, just hilarious. He'll give it a go. He doesn't know what a coupled oscillator is. No hope. Okay. Not sure how much I will be able to stomach, though. Thanks for the heads up on this. So isn't it kind of just bizarre that he needs a heads up? I make a video every fucking day. Right? It's really not that... You don't sit around for 2 weeks and, oh yeah, I forgot to check, No, there's one every fucking day. I mean, just amazing. Oh, God, these people are such pieces of shit. All right, so... enough of a video. I mean, just, it's just... there's so much, like I said, I didn't see idiocracy coming, I didn't think the world could get as silly as it is. I never would have predicted the corruption, the level of corruption. It just, it makes Watergate look ridiculous as a crime. I mean, it makes, things have gotten so fucking bad. And yes, I would have never thought that having a physics argument would entail all of this nonsense. It's just amazing. And a physics argument that's so obvious that this is really bad science that they're guilty of. I mean, that these weasels, Puro and Mindless and all these assholes, can't admit that it's really, really depressing and ugly that science hasn't done any of these experiments. That they've never proven this 1/2 mv squared thing with real experiments. Nowhere. They've never shown you 9 times the fuel to go 3 times faster. They've never done the experiment. 9 times the damage going 3 times faster. They've never shown it. They just preach it. They're telling you the 8-pound bowling ball going twice as fast knocks down twice as many pins. Never shown it happening. Ever. Nothing. And these weasels talk with this kind of arrogance when this is the science they're defending. The science that looks just like a religion. Fuck evidence. This is about fun. This is fun physics. 1/2 mv squared is fun. I can dance to it. That's all they're saying. Doesn't matter that it's shit as a theory. God, I hate this planet.